Alright, now we're going to talk about the calculus of exponential and logarithmic functions. And we'll start off saying a few things about exponential functions and the number e, and then we'll get into the calculus. E, as you may recall, can be defined like this. It's the limit as n approaches infinity of 1 plus 1 over n to the value of n. So if you take this expression and start putting in values for n and doing the arithmetic to calculate a value for that expression, as n gets really huge, the number approaches this number that we call e, and e is approximately 2.7182. And you can actually see that value if you graph this mathematical expression as a function. So we'll pull up the calculator here, and you see I have the function entered there for y1. I have 1 plus 1 over x to the power of x. I'm using x instead of n, but that's okay. And if I go to a standard zoom setting here, you can see it graph the function, and you can see a horizontal asymptote there. And the value of that horizontal asymptote is e, 2.7182. So if we were to go way out to the right, for example, on this graph, and we can do that if we hit trace and just start going over to the right, you can see as the x values get bigger, our y values are they're over 2 now, and it's getting up to about 2.5, and it will gradually rise, but rise more and more slowly, and it will slowly head up toward that number 2.7182. And if you went way out to the right, it would get closer and closer to that value 2.7182, and so on. Now this number 2.7182 is just an approximation. These digits really go on forever. It's a non-terminating, non-repeating decimal, and it's similar to pi in that it's an irrational number, and it's also a number that shows up naturally in the real world. Just like pi shows up wherever we deal with circles, e shows up wherever we deal with exponential growth or exponential decay. And it turns out that a tremendous variety of natural phenomena, things that we see in the real world, can be described by exponential functions with a base of e. In other words, we can mathematically model a lot of real-world scenarios by using this number as the base for an exponent. And here are a couple of examples. One is radioactive decay. If you have, we'll say A is some amount. You have some amount of a radioactive substance. That's going to be equal to some initial amount times e to the kt. And this k here will be a negative number indicating exponential decay. And it's decay over time. You see the t right there brings time into the equation. As time gets larger, the value of this factor gets smaller because the k is negative. Another good example is population growth. And this is an example of exponential growth, not exponential decay. We would have a function something like this. The population is equal to the initial population times e to the kt. And k here would be positive. So as time went on, this factor would get bigger and bigger. So we're raising this number e to a larger and larger number. And the population then is getting bigger and bigger over time. And the thing to realize is that when you have exponential growth, the rate of growth depends on how much of the thing that you have. So for example, say you have some bacteria, a population of bacteria. The more bacteria there are, the more bacteria there are reproducing. So the rate at which the population grows depends on the size of the population, and as it gets bigger, it grows faster and faster. And most people don't really appreciate the power of exponential functions. These growth rates can really get out of control over time. Exponential functions are extremely powerful in that sense. In fact, the physicist Albert Bartlett put it this way. He said, "The greatest shortcoming of the human race is our inability to comprehend the exponential function." And so our goal in the coming pages is going to be to remedy this shortcoming of the human race. Now E, incidentally, the number E there, E stands for Euler. And here's a picture of him. This is Leonard Euler. He was a mathematician. He was from Switzerland, lived in the 1700s, and that's Euler. And just a phenomenal mathematician. Did a tremendous amount of work in a wide variety of areas and a lot of very significant theories. In fact, his name is on so many different theories that there's a saying that a friend of mine told me once. He said that mathematicians are in the habit of naming their discoveries, and you know this. Say for example, the Cauchy-Schwarz inequality, named after Cauchy and Schwarz, who figured it out, or the Pythagorean theorem, for example, named after Pythagoras. Well, the saying goes, mathematicians are in the habit of naming their theories for the first person other than Euler to have discovered them. And the joke is there that people figure something out only to find out that Euler had already figured it out before them. He figured out a tremendous amount of math. You see in this picture, his right eye is squinting there. He was nearly blind in his right eye. He had an illness in the early 1700s that almost killed him and left him nearly blind in his right eye. And then later on, he went completely blind in his left eye, and he was left with very little sight at all. But he continued to be just phenomenally productive. He had a photographic memory and would work with the aid of scribes. And even in later years in life, he was producing up to one new mathematical paper per week. Just a tremendously productive individual. And he's without a doubt the greatest mathematician of his era, the greatest mathematician of the 1700s, and one of the greatest mathematicians of all time.